All right, so we start our very formal workshop. So it's a great pleasure to introduce Pedro Muniz, who is going to tell us about GKM approach to conclusion the policy. Pedro?
Thank you so much. Hello, everyone. My idea here is to show a joint work with Giovanni, Leonardo, and Ludmil. And the idea, at least my part, was to build a software to compute the probability invariance for flag manifolds. And for this, we use an approach in defining these flag manifolds as GKM spaces. And the goal of the project is to be able to compute the eigenvalues of the small quantum multiplication composed with the Euler vector field. Well, my idea here is to give, this is the first talk of Giovanni's talk tomorrow, but my idea here is to define Gromov invariance, talk about the variant Gromov invariance, and explain why GKM spaces and what are they. And the talk, I will talk about complete intersections, and hopefully I will have time to show some of the computations that our software can do. And this type of. Well, let's start with Gromov invariance. Here I'm going to give a more axiomatic version of the definition of Gromov invariance. But the basic setup is always a smooth project variety, and we take beta, an element in the homology, an effective class, in other words, a class that comes from a curve, a curve, and we denotify MEX, the modicon, that is the common effective class is only 2, and we will denote a tuple like this. We will call that divisible if the class beta in homology is different than 0, en, or n, the integer, is greater or equal than 3. We define what is a Gromov class as a class in this homology group in the product space of x times x, n times, and this delta is this guy right here. Okay? And that will be then here in the homology class plus the dimension of x as a complex manifold, minus 3 plus this integral of the first term class in this homology. And we can define the Gromov invariance between these classes in cohomology as this integral, where py is just the projection on x on the times x to x, the e projection. Here is just the ordinary product, and here are the cubes. Okay. Well, this is not the usual definition of Gromov. We are not talking about the modular space of stable maps, but in fact, and if you look at this, it may depends on the choice of the Gromov classes. However, if we ask some axioms from the Gromov classes, we can recover the classical Gromov theory using still the modular space of stable maps. This is going to be this is going to appear in these lectures. 9.5 lectures on atoms by Kaehler, Ludmil, and Maxim. Well, about how to recover the original definition of Gromov, it's quite simple. If you first, let's talk about the modular space of stable maps. Okay, by stable map we mean a genus zero stable map is a map from C to X where C is a projected connected nodal curve of genus 0. And these points are smooth marked points on C. Smooth in the sense that they are not singularities in the curve. And we ask that the automorphism group of F is finite. Here is the automorphism of F as a marked curve, a marked map. It's an automorphism of C, but that respects the marked points. Okay? And we will denote by this guy right here the modular space of stable maps such that the push forward of the fundamental class of the curve C is equal to B. This is in fact the line of stack, and the virtual fundamental class is a guy right here. It's a guy in this homology group. Okay. And I'll recover the usual Gromov theory from the definition that I gave. before. Well, considering the evaluation map that goes to the modular space of stable maps to X that just pick a curve and evaluate that in the E market point. So hence define this evaluation map, that's just the product of all the evaluations and all the market points. Then you have a map that goes from your modular space to X time X and time. Then this Gromov-Witten class is just the push forward of the fundamental of the virtual class that I showed you earlier. In this way, we can recover the usual definition of Gromov-Witten theory that you have in a lot of books. It's just the integral over this fundamental class, and here the projection is the evaluation maps. You just go back, this forms on again here to the modular space, and you have the product. Now we have the Gromov-Witten invariance, and we can define what is the Gromov-Witten potential. Again, for a smooth projective variety, we define the Gromov-Witten potential as this series right here, and we sum as beta in the naughty column, and the marks here, and the n times gamma. For a form gamma, you take n times gamma. Okay, this is the Gromov-Witten potential, but you can write a form in homology. If we choose basis for our homology, like this P0 being the identity generator of H0, and this guy is right here, the generator of H2, you pick a basis of your entire homology, and you can open a generic element as a sum of this type. Okay? Just in like in the coordinates. Hence, it's possible to open the Gromov-Witten potential in these coordinates also. Okay? And when you open the Gromov-Witten potential in these coordinates, you can divide it in a classical part and a quantum part. The classical part has this expression right here. Look that the Gromov-Witten invariance doesn't play a role here, only the usual cut product. And in the quantum part, you have the product in the Gromov-Witten invariance. Note that here we have this variable Ty that is in fact this integral right here of Ty, and Ty is a form on the second homology. On the second homology. In this case, this happens because from the axioms of Gromov-Witten, from the properties of Gromov-Witten, you can take the elements in the second homology outside using the divisor axiom, and it goes out like this integral right here. We just use the variable q to simplify the expression. Okay. Well, now we have the expression of the Gromov-Witten invariance in coordinates, and it's possible to derive it formally. Hence, we can define what is the big quantum product. The big quantum product is interesting because today we are interested in the eigenvalues of the big quantum product composed with the Euler vector field in order to compute atoms and this kind of stuff. I think Leonardo will talk about this later, and Giovanni also. But if we define this pairing on the cohomology in its term X, we can define the big quantum product as these derivatives, the stern derivatives of the Gromov-Witten potential in this coordinate that I show you, times this pairing, this T times T. This product here I define it on the basis of the cohomology, but you can extend it to all the cohomology. And this product is associative, commutative, and have a unit. And it's possible to consider this area here. That's just the cohomology transferred by this formal power series in this coordinates also. And we call this ring with the big quantum product as star the quantum cohomology of the space X. Okay. Well, it's really hard to compute the big quantum product. However, it's possible to compute the small quantum product. That the only difference versus here we define it like this, and we consider only classes on the neural form. Okay, the model form. Again, this product, this small quantum product, is associative, commutative, and have identity, and it's possible to define a ring with the guy that I showed in the slide before. And this ring is called the small quantum homology. The small quantum homology we can compute, and the idea was to build a program that is able to compute the small quantum, the eigenvalues of the Birational class composed with the small quantum product for flag method. This is the talk of Giovanni's model. So now let's talk about equivariant Gromov-Witten invariance. The problem is it's really hard to compute Gromov-Witten invariance, but with some luck, if we consider the equivariant version, a version that is invariant by the action of like a torus, it becomes easier in some sense to compute. Again, consider X as smooth projective variety and beta a class in the second homology. And we consider a T action, where here T is just the algebraic torus on X. With a T action on X, it's possible to induce a natural action on the modular space of stable maps. The action is described right here. You just pick a curve, a stable map, the modular space, and you compose with the action on X represented here by T. Again, it's possible to define what it means to have a T equivalent ETH evaluation. Is just a E evaluation, but is equivalent is invariant by the action of the torus. And with these two informations, it's possible to define what is equivalent Gromov-Witten invariant. The definition is quite simple. It's quite similar, but it's quite similar to the definition of the usual Gromov-Witten. But here we consider the T equivalent E evaluations, and we use this T equivalent integral. This T equivalent integral, as you can think as integrating in the fixed locus by the action of the torus. And note that here we take forms to apply the Gromov-Witten in the equivariant homology. This guy doesn't give a rational number. It gives a polynomial in these coordinates that are the characters of the action of the torus. And it's possible to recover the usual Gromov-Witten, letting these parameters to zero, this polynomial to zero. This if we have a space that this fixed locus by the action of the torus is simple, it should be easier to compute this invariant. Maybe it's possible to compute it. And this is what happens in JKM. In JKM spaces, the fixed locus by the action of the modular space of stable maps becomes simpler, and it turns like it's a problem of combinatorics in graphs. It's you reduce this integral for some. This is why we consider JKMs. Now let me define the two JKMs and show you guys the explicit formula to compute these invariants in this case. We say that a JKM space is a smooth projective variety with an effective T action, again the algebraic torus, if the fixed locus is finite and the one-dimensional orbits are isolated, are P1s inside it. There is a lot of spaces that are JKMs, like Pn is JKM for ON, toric varieties, Birationals, and homogeneous spaces. Okay. When you have a JKM space, it's possible to extract the JKM graph that has a lot of information about the space, and you consider a graph associated with the space where the vertex are the points that are fixed by the action of the torus, and the edges are the closure of the one-dimensional orbits, are the P1s inside the space. Here is an example. P2 is a JKM manifold. You have the torus. You consider as the algebraic torus, C3, and the action in P2. You consider an element in P2, like this. And a guy like this. act on it. Just guarding. Okay. The fixed locus of this action is just 3 points that are here denoted by P1, P0, and P2, and the one-dimensional orbits are just these P1s here inside that goes to P1, to P0, to P0 to P2, and this is the GKN graph of P2. Okay. Well, with the T action on the manifold X, we can induce the natural action on the modular space of stable maps. And in fact, it's possible to describe this modular space of stable maps. For this, I will need this definition of what it means for a tree to be n-marked for n image. A tree is n-marked if the set of the vertices are finite, and the edges are subsets of this guy right here that goes from one vertex to another. We have a map that marks all the vertex of the tree to go into 1 to n. That's represented by this guy. This other map identifies a vertex on the tree with a fixed point by the action of the torus in space, and another map that identifies an edge with an one-dimensional orbit of the T action. Furthermore, we have degrees on these trees, and the degree is associated to the class of the irreducible component of the curve when you push forward it to the space and equals to b. This is a marked tree, and it's possible that there is a bijection between the fixed locus of the modular space of stable maps and this kind of trees with some properties that I will explain. But given an element in the fixed locus of the modular space of stable maps, it's possible to construct a marked tree as I showed earlier in the following way. To each point in the fixed locus of the action of T on X, we corresponded to a vertex, and we mark the vertex with E if it is a marked point in C. And the edges of this vertex, then the edges of this tree, it will be the reducible components of C that are P1 that goes from one vertex to another. And we have the degree that is just the degree in homology of the reducible component when you push forward to X. Well, from this bijection, we have a complete description of the fixed locus of the modular space of stable maps. Then it's possible to reduce the integral in the equivariant probability invariance to just a sum in those type of trees. Just in order to me to show the result of how to compute this invariant, I will need just some definitions. If we have a point, the fixed locus by the action, the tangent space is decomposed in one-dimensional two spaces like this, such that the torus acts on Txy, the torus acts on Txy, with a non-zero character that we will denote by lambda xy. This guy is in the algebra of the torus. And we will denote by S a equivariant lifting of the cohomology. This is just a section of the usual projection in this guy, the equivariant. Well, it's a lot of expression. The expression is really big, but it's finite and it's possible to compute. If we have a GKM space, and we have a choice of splitting, as I showed earlier, equivariant lifting. If we take n forms and elements in the cohomology, it's possible to compute the equivariant removal with the invariance between these guys, like this sum right here. This sum is over trees that satisfies the property that I showed earlier. The sum of the edges and the classes are equals to beta, and it has any market points. In market trees. Well, this guy omega of the tree is we call it the weight of the thing, and it has this expression right here, 3D. But I will just show this guy the next slide. Here, the KV is just the sum of all incident edges in one vertex plus the number of marks in this vertex. Well, the formula of H is this one, and the formula of the other part is this, and the U expression is blank. Here, EV denotes the number of edges inside one vertex. It's ugly, but it's finite, and it's possible to put in the computer. And this is what we've done. But this is just to show that the formula works. If we have P2, let us use this formula to compute how many lines pass through two genetic points in P2. This is the same as computing this gamma-quickening value, where P is a form in the top homology. And we will consider this equivariant lifting right here. That's that choice of section. Well, beta is equal to 1. The graph of P2 is like this, and beta equals to 1. There is only one type of tree that we need to consider in the sum, that are trees like this, with all the markations possible. And what are all the markations possible? We have P0, P1, and P2. And here, C01, C12, C02. There are only 3 possibilities for the edge. The edge only at 01, or 02, or 12. Okay? And you have the weight, but the weight only can be 1 because it needs to sum and goes to beta, and beta equals to 1. Then it's easier. The formula is a sum of 6 guys, but we reduce the 6 guys because we have 2 markations. Hence, each of the trees you can mark 3 ways: 2 points here, 2 points here, or 1 point here, 1 point here. But we reduce this and include all these computations in one of those terms right here. Okay. This is the weights of the action that I showed earlier. Then if we compute all the contributions come from graphs of this type, with all the markations possible, we have the expression, the second one, and the third one. And this is equal to 1, exactly as should be. Another example, now that we use the software to compute, if you have FL3, that is the maximum flag of A2, right? Yeah. The maximum flag of A2. The gamma-quickening variance between gamma 1 and gamma E, gamma J is equal to this table right here, when the form beta is equal to alpha 1. This means what? What this means? The second homology of this flag.
Can we go forward?
Okay.
Gamma, this picture.
Okay. Let me. The homology of this flag is H0 plus H2. Correct me if I'm wrong, Giovanni, please. H4 and H6. This guy has only one generator. That is, I call gamma 6. This guy has two generators, gamma 4 and gamma 5. This guy has 2 generators, that is gamma 2, gamma 3. That coincides with the root system of the flag. Giovanni will talk about this later, but this is alpha 1 for us, and this is alpha 2. Yes, alpha 1.
Yeah, just the point that in flag varieties you have a preferred basis for cohomology. So the gammas are just they just vary the gammas basis and compute the gamma-quickening variance.
So the first diamond is 1 to 2
Yes.
So these gammas are sugar cells.
Yes. These gammas are dual to the sugar cells.
Somehow the word sugar. I apologize. More than 100 years ago, that's what people would start.
For both.
No, the Schubert.
At the end of the day, until now, this is nothing else but enhanced linear algebra, so quantum multiplication.
Yeah. But in this basis right here, we can compute the Gromov-Witten invariance through the software. And this is the result for beta equals to alpha 1. That is just this generation here in A2. And this is the Gromov-Witten invariance, the same ones, the two pairs. And here that beta is equal to alpha 1 plus alpha 2. The generator that the element that is just the sum of those two. We can do a lot of examples of this. I just put the two Gromov-Witten invariants of between two cohomology guys because the matrix will be very large and the program will take a time to compute. This is one of the problems that we have right now, but we need to improve it. That the time for computing these things.
So did you do this? Did you write the code by yourself, or is it available somewhere? Or?
No,
It'll be available soon. We still need to.
So you're writing, or
Yes,
you're
right. It's already computed. Some cases you just need to finish to compute all cases. Right, all right.
So can you go back, Pedro?
Okay.
So now, what is this matrix represent for these two Schubert cells?
Oh, okay. Well, this guy is this Gromov-Witten invariant. 2. And beta equals and beta alpha 1.
This is not the quantum multiplication.
No, it's not a quantum multiplication.
It's just the Gromov-Witten invariance.
Are
Most
just
of them can read, just read the letters.
So the first
Oh.
entity is the Gromov-Witten of the two classes of the identity.
yeah.
The 2-point Gromov-Witten invariance.
The ID.
Yeah. So the AJ entry is the 2-point Gromov-Witten invariant of the class gamma I, gamma J, for the choice of beta alpha 1.
I just computed two Gromov-Witten invariants just to it's easier to show to you. But it's possible to compute and multiply.
And 92. What's that out? 92.
Oh, the number of attempts probably. No, the lines in the code.
We don't have an interface yet. It's coming
But
soon.
User friendly.
Yeah. Well, this one is the same matrix, but now the beta is alpha 1 plus alpha 2. We have a lot of zeros. And this another example, another flag. This is the flag, the maximal flag, which I don't know if you guys know about thinking diagrams, but is this the algebra B2? This is the maximal flag. You can think as SO5 modeled by the Borel subgroup. Again, this is the matrix of two correlators. Here, the cohomology class is generated by with our thinking, it is generated by the Schubert cells. And this is the matrix for beta alpha 1 and for beta alpha 1 plus alpha 2, alpha 1 plus alpha 2. And yeah. Well, now I want to talk a little bit about complete intersections, because the idea is to now compute the Gromov-Witten for complete intersections in flags. There is a lot of parts that can be thought as complete intersections on flags. I will show some examples. And we have a formula for the Gromov-Witten invariance, the sum of some Gromov-Witten invariance in this case. Well, again, X as multi-protective variety, and we will denote E to X a vector bundle that is generated by double sections. If you take a section that intersects the zero section transversely, it's possible to define what is a complete intersection, and it's just the zero locus of the section S. We will denote by Y. Okay, and this is for us is the complete intersection. Okay. Well, denoting I, the canonical inclusion of Y in X, and beta, a class on the second homology of X, we have this relation between this modular space of space on X. And this is an inclusion as a closed subspace. Then it's possible to use the formula that we have for this modular space, the identification, use the T equivariant, the fixed locus by the action of T in this guy to derive a formula for the invariance, for the sum of the invariance in this set. For this, I will need just some definitions that will be given now. Now, if X is a smooth projective GKM spaces, and we asked that the vector bundle that I told you earlier is also equivalent by the action of the torus on X, and in a fixed point by the action, we have this splitting of the vector space, the fiber of the vector space, in a sum of one-dimensional spaces, such that the T action of these guys have weights that we will denote by mu xy. Again, in the algebra of the force. In this case, we also have a formula, but now it's a sum of homologating invariants. And again, it's ugly, but it's possible to compute, and we can put in the computer. And the only difference from the formula that we have for the homologating invariance to X is this term right here, that is a complete intersection term, that is computed exactly like this. Again, the valence of V is just the number of incidence edges in the vertex V. And the expressions, oh, sorry. And again, this is the equivariant homologating invariance, but we can recover the usual homologating invariance just letting the parameters, the polynomial parameters to zero. Here, this HA, this formula right here, this BCL term is just a number that appears, and you have is a natural number that appears in this expression. When this guy right here is just the weight in the fixed point, and this is the weight in another fixed point, but the curve, the curve C, the edge C, take this point. This is the zero, this is the infinity, this is the C. Okay. This is the weight of this guy here, and this is equal to B, CL, in the weight of the action on X. And the Euler P has this expression, the simpler expression. And again, the idea is to implement this formula and computing the sum of homologating invariance in this case. Well, one example is K3, famous surface. It's possible to think it, to thought it as a complete intersection in FL3. And you choose the vector bundle as the canonical vector bundle on FL3. Then the complete intersection gives you the K3 surface. And this is the matrix of the computation of this invariance right here. Again, we are using the identification with the
Okay, so what's the geometry? Yeah, so
These guys will be the Schubert cells again. Okay,
The pullback.
the pullback of them. The problem here is we don't know
what's the dimension of the before we take the
Then it should be. So this is K3 surface.
just a what? Okay, this can be
No, flag it.
the flag has dimension 6 and
Real dimension 6.
real
complex
dimension 6, complex dimension 3.
The P1 bundle of the fabric. Then we pick that canonical bundle.
well, this is the 1, 2 divisor in this so it's a conic bundle. So this K3 has got to. Okay. Okay, that reports the yes.
Well, here the K3 has complex dimension 2 and has real dimension 4 and has 4 cohomology groups, but in this matrix right here, we are only considering this guy and this guy on the zero cohomology and in the first cohomology. It's possible to consider in all cohomology of Y, but the problem is by the left hyperplane theorem, there is an isomorphism between this guy, the cohomology of this guy, and the cohomology of this guy for Y less than n minus 1. And the dimension of n is here is 3 minus 1, 2. Then this is isomorphism happens for all p equals to 0 and 1. Then we can describe these guys easier. But it's possible to do more generally. So we're free. And this is the matrix of the sum of cohomology invariants for these two guys, all zeros. And this is the matrix. Now considering a del peso of degree 6, we can think this del peso as a complete intersection again in FL3. And this is is a complete intersection in FL3, and we take the vector bundle as the square root of the anti-canonical one. That's the
Then we say it's just hypersurface, not complete intersection.
Okay.
Because we're picking only one line above.
oh cool.
That is the square root of the canonical.
Oh.
Hypersurface.
Okay, hypersurface in FL3. And again, the same happens by the left hyperplane theorem. This guy is equal to the homology in the ambient, and here we compute the this sum of the Gromov equals for this the beta equals 12 to 1, and here we have an entry that is not zero. That's why I choose this invariant. Well, I think this is all. The next step is to consider Giovanni will show you guys that we can compute the eigenvalues of the small quantum multiplication composed with the first chain class, and this is the idea because the bank always try to talk about that, compute some outcomes in some cases, and talk about maybe of G not directionality with the G action. But this is all. Thank you.